Yeah, so I will be presenting a little bit about some of the discovery opportunities with radio surveys, particularly the one which are already come up in some level, and this will be mainly for the two radio telescope which we all know, the Square Kilometer Array and the LOFAR in the Netherlands. And some of the data or the images taken with these telescopes are already made available in the public domain, and many people are using it, and a number of discoveries have already been made. So particularly if you look at some of the numbers here, the Square Kilometer Array, there are a few small area surveys like EMUPS in a large area like this rapid escape survey at close to 900 megahertz is achieving about 250 microjansky per beam with a 25 arc-second resolution. And that's a very good for the southern hemisphere where there is not much, such a high resolution survey where available. LOFAR is doing in the northern sky, and the advantage is that it's a very low frequency, 144 megahertz, where very few good images, large sky were previously available. And we all know, or if anybody has worked with the LOFAR, we come to know that this is a very excellent images which it is producing at 80 microjansky per beam. And in addition, this is also giving the full polarization data. So that's very important. The resolution is about 6 arc-second. So that's a really unprecedented, which was not available before. So if we look at the two surveys comparison, just a quick comparison in the southern hemisphere, the earlier images which we had were from the SUM survey, and the ESCAPE is now putting the same, the reason. And we look at that it's not just the sensitivity, but also the angular resolution, which is extremely important in making, detecting new sources and also looking at the morphology thing. So what is the highlight of this talk? Of course, we all know that with such a great sensitivity improvement, both in terms of the flux and the angular resolution, many discoveries have already been made with the data which is available in the public domain. What I'm going to highlight here is some science cases in which I was particularly involved. So I'll present those. And one of the major highlights of doing science with this survey is that they provided excellent tools for visualization and how to access the data. The archival part is excellent, and that's why I think one can do it very quickly. So let me just come to the first one, which hit the news about 2 years ago. That is on the odd radio circles or ORCs. These sources are circular ring-like morphology. These are very low surface brightness, something like few tens of microjansky per beam. They were first detected with the ESCAPE EMUPS survey. And some of the sources then also in the GMRT archival data, one of the source was detected. And then there is a follow-up with the MeerKAT with high resolution. So what you see here is that these sources are fairly circular and they are edge brightened. Okay, if you look at this. Okay, and this is the MeerKAT image, which actually shows very clearly that these sources are quite a lot edge brightened, and there could be multiple rings also. So that's why these were called the odd radio circles by the discoverer, Ray Norris, because such morphologies cannot be understood by any known existing kind of sources. Of course, there is a lot of discussion given in their discovery paper. They rule out by many arguments why it cannot be radio galaxy, why it cannot be supernova in the galactic and all that. So one can look at that detail. Now, what is interesting that in some odd radio circles, a galaxy in the center has also been found. So that makes it very interesting that whether it's truly extragalactic or not. And so if you look at one of these well-studied ORC, then if we associate that the galaxy which is seen in the center, so this is a radio image overlaid on the optical image, Then looking at the photometric redshift, which is available for this source, if this is about an arc-minute source size, the source extent, physical extent, become about half megaparsec. So if we believe that is the galaxy associated and the redshift is accurate, then these are really of the size of megaparsec. The thing is that they don't look like a typical galaxy cluster, halo emission kind of thing. And also, these galaxies are not the cluster galaxies. I mean, this is not like any central cluster galaxy, and there may be some other density enhancement, but this doesn't look like a cluster environment. So these were the discoveries from the ESCAP survey. Now I looked at some of the images. And we found one more odd radio circle at 144 megahertz with the LOFAR. Again, the morphology is circular, although it's not exactly as enhanced, but there could be the resolution issue also here. So this is also qualifying for what we call the odd radio circle. So this is a point here that we do not associate ORCs presently with any particular type of source. This is only a morphological class of objects. So anything which is circular, edge enhanced, we have to flag it. We have to find later on that what these are. This could be radio galaxies also in some projection. We do not know. So any ORC kind of morphology is very rare. That's what we have seen, but not extremely rare. So we are able to find it in few images. Just look at 5 or 10 images, you are able to find one ORC. And so the first thing, when we look at the ORC, it definitely appears like a supernova remnant. We know that the supernova remnants have a very similar morphology, but the issue is that by looking at the number of ORCs, so about 7 ORCs are known in a very small area which has been surveyed. The problem is that these cannot be galactic SNR because most of the galactic SNR are concentrated within the galactic plane. We do not find it at high galactic latitude, while these ORCs have been found at high galactic latitude. And that's because the survey has been presently done at high galactic latitude. And this cannot be explained by the normal population of galactic SNR because we just don't find any, hardly any supernova at such a high galactic latitude like 60 degrees or so. And so this is the paper which I wrote in MNRS Letters that proposing that this could be intragroup medium supernova remnants. So these are like truly intergalactic supernova remnants, which have been discussed in the literature, but very rarely. And that's the reason because this was very thought to be very difficult to detect because of low surface brightness. But now these surveys have come, which are breaking all the barriers in the surface brightness. We are achieving tens of microjansky per beam, and that's why they have become detectable. So this paper actually presents that analysis that these could be very well the intragroup supernova remnant. There is another interesting thing about ORC, that the ORCs which are detected with a galaxy in the center. So the point is that not all ORCs have galaxy in the center. So the ORCs which don't have galaxy could very well be explained by intergalactic supernova remnants. But those ones which have a galaxy, it was found that these are post-starburst galaxy, and these are not associated with any star-bursting radio halo, which has been seen in other, nearby galaxy, for example, NGC 253 and all those very highly starburst galaxies. This is actually a quiescent galaxy right now, and such a large halo in quiescent galaxy is even more surprising. Okay. So the post-starburst galaxies are those which actually experience a starburst about a gigayear or so, but these galaxies are not evolving, actively now. They are just evolving passively. So it's a very difficult then to understand how such a radio halo, synchrotron radio halo, could be formed around a quiescent galaxy. So if you just look at the energetics required, in very simple terms, if it is just an expanding shock, then the typical energy required to create about a half megaparsec structure in intergalactic medium, we need a energy which could be like 10 to the power 55 to 10 to the power 59 ergs. And there is a range because if you look at whatever 5 or 6 these such objects known, some of them require less energy, some of them require very high energy. So this is the range coming from whatever we know at the moment. And that means If we consider about 100 million years for the synchrotron age for the radio emission in typical intergalactic medium or intercluster medium, this energy input rate is of the order of 10 to the power 40 to 10 to the power 43 erg per second over this short period of time. Okay, and that is definitely much higher than what a supernova can produce. Okay, and so this is not actually related to any kind of previous starburst phenomena. That's a very difficult that this will be seen at the present epoch. And so this was the idea which I put in, that one of the mechanism which we know can produce large energy even in a non-starburst galaxy is tidal disruption event. And we need actually a large number of tidal disruption events to do that. And I will just not get into detail of this, but people can look at this later paper. What is here, what I propose here, if you look at the basic theory of tidal disruption event, there are two things involved. One is the tidal radius, other is the Schwarzschild radius. So the tidal radius has to be larger than Schwarzschild radius in order the star, when it crosses, comes in the close vicinity of the black hole, has to be tidally disrupted. If the Schwarzschild radius is higher or equal to the tidal radius, then a star will not be tidally disrupted, but it will be completely, taken into the black hole. And so that's why the tidal disruption events are more, prominent in case of low, the low mass black holes. For example, typically, if the black hole mass is less than 10 to the power 8, there is a very high chance that it can undergo, a kind of tidal disruption when a star wanders near it. In massive, supermassive black holes, this event will not be seen. So TDs will be very rare. And so it explains that this could be actually seen from some of the low mass galaxies where the black hole mass is not really very high. So this is the typical picture which people who work on TD will recognize, that when the star comes, it is tidally disrupted, and then about half of the mass become the bound, and about another half is unbound, which is thrown away at very high speed, because it gets very high speeds when it comes very close to the black hole. Closer it comes to the black hole, higher the speed which it gains, and there are parameters for that how close it actually passes through, how elliptical, the is the orbit, right? And so this energy distribution in the unbound debris, this is just the kinetic energy which every ejecta here gains. There will be a distribution of energy, and this is out of the simulation for one solar mass star, that the energy range will be distributed over a huge, for example, 10 to the power, let's say 10 to the power 47 to about 10 to the power 51 ergs. And that's very interesting, that some of these ejecta can definitely reach an energy which is what we see in a supernova event, which is a typical energy at 10 to the power 51 erg. And so that makes very interesting that if now this is for one solar mass star. Now, if there are massive stars, the energy will be multiplied by that amount. And so this is very interesting that some of the TD can actually do that. Now, only problem is that when you look at the TD rates are very low in our galaxy. But it is known from the simulations, these are references here, that when the galaxy merger happens and there's a post-galaxy merger, the TD rate becomes very high. It could be like 1 per year, or about 10 to the power 6 per million year. And that means if such a high rate of TD can happen in a very special condition after the post galaxy merger, when the black holes are coming closer to each other, and then they are actually crossing the disk, and that's why there is more higher chance that the stars will we get into the black hole, and that it means that the total energy can actually power up in certain conditions to these ORCs. Now, the thing is that at the moment...
Sorry for the disruption, Amit. It's about 3 more minutes.
Okay. So we looked at the back, thing that, okay, can we look at the galaxies which are tidal disruption events, and from the LOFAR data, and do we find any radio emission around those tidal disruption event galaxies? So we were lucky that there were 23 TD host galaxies were available in the present LOFAR survey. And in fact, 2 galaxies showed up diffuse emission around that. Again, these are not starbursting galaxies. These are just normal, passively evolving galaxy, and we do see halo around that. So this actually puts some strength to what we have said. Now, I will just quickly go through, and these are all published work, so people can look at that. And this is the most recent one where I have shown just a very rare kind of FR1 jets in a low luminosity NGC 5322 galaxy. Earlier, only the central emission was known from all the survey, including the GMRT. And this is a very faint emission which you see in a large scale, which is sort of just uninterrupted. It is going. So this is something very rare, and I think such kind of with low energy this size has not been detected. And so that makes a very interesting case of looking for such galaxies in this survey. Now, some of the work which is under progress, I'm just flashing it. This is a very complex morphology radio source which we have found in LOFAR, and there is an optical in the thing. This is not a cluster source, and so this becomes very difficult to understand. Presently, we think that this is a radio galaxy seen face on, particularly the one which we call the fat radio galaxies. So this could be one of those rare galaxies which can be detected. Now, just the last two slides here. Why we can actually do this work in a very short time is because I believe this is the excellent visualization tool which these surveys have provided. For example, you can just browse these images very quickly on your any web browser. For example, here you see there's another discovery which we have made here. Is a very small jet, and there is a very large radio halo around a galaxy. This is again not a cluster source. So this is all individual galaxies which are showing up very large halo. So the point here is that it's very good that these surveys have provided excellent visualization tool which makes anybody to look at the images quickly. I mean, remember, these are very large data sets of the order of terabytes and petabytes of data. So one would not like to download it first and then look at that. And I think the survey team, is very good in this process. That if they want to distribute the data and wants everybody to use it, the visualization was an important part of it, and I think they have done it excellent way. Very last point which I want to make here: these images were searched for using the machine learning algorithm which were made by these people, but we found that none of the those searches actually reported these complex sources which were presented just in this talk. So it's very important that to note that all the machine learning and AI approaches which are presently existing on these surveys, they do not actually discover very faint complex radio sources. It still has to be improved quite a lot, and that makes a case for individuals to work on that. Means that the data, whatever has been provided, it is still unexplored for complex faint sources detection, and it definitely are waiting to be discovered by people, and that makes actually an excellent opportunity for people who are doing citizen science based approach. With that note, I finish my talk. Thank you.
Thanks, Amit. So questions from here. Yeah, Rashid.
Hello, thanks for the nice talk. So I was wondering this ORC, how the tidal disruption model can give the energy injection scale, but how it will explain the morphology of the ORC?
Yeah, so for the details you can look at the paper, but it's very similar to that. Millions of such events are going on within the synchrotron lifetime, let's say. So these are the shocks, okay? And the shocks are so this is accumulated, energy in the shock very quickly, and that can just move out in the intergalactic medium. So this is the shock which is, generating the synchrotron radio emission.
Stalin?
So if it is a TD, do you expect to see some flaring behaviors in the sources?
Sorry, can you repeat this? The flaring you said, right?
So do you see time variable phenomena in these sources?
Yeah, this is I think a very good point. So that has not been explored. Only 5 or 6 sources are known. So it's a very good that these objects should be looked at, for time variability in the AGN. Nothing is known at the moment.
So one more question, what is the environment of these sources?
Sorry?
What is the environment of these sources?
I'm not able to hear.
Environment of these sources, is there any
Environment of these sources, they are not in a cluster environment. These are just probably small groups. And these are not a very high mass galaxy. And the black hole masses are low. That's known in some cases. So that is all we know at the moment.
Oh, thank you.
last question maybe, Sagar? Oh, okay, it's already answered. Okay.
Just one question. Have you looked at the optical counterpart behavior of these sources or no?
Yes, I think optical counterparts are known. Only there is not much information. For example, not even the spectroscopy is known because these are faint sources. So there is a lot of optical side, a lot of work has to be done in this case.
Long live India and France friendship.